Hi there, welcome back to tutorial 8. So in this tutorial we represented, and this is the classical external aerodynamics NACA 0012 airfoil. So if you go to the website, you already download the file, so you should have that structure similar to this one. Probably less file here have more sense that maybe you don't need. But as usual, here you will have different meshes. Already discussed this one. So we go to the Fluent case and see that we have 3 different directories, different mesh data structure. Okay, so I will go and open the first mesh, rectangular domain. Okay, so you see here that you have 2 different files and also the supported data for validation. So let's go there and open one case. So Fluent case, we go for rectangular data, and I will go this one, 4 dec, which means 4 degrees. Okay, so before starting, I just want to remind you what we're going to do. It's just basically this classical case, and something very important, we're going to do it when setting the case. Remember, when computing the forces, you need to adjust your axis here, your reference axis. Okay, so you have 2 actions. You can change the angle of the physical angle of the airfoil. Okay, you can put it at 4 degrees or 10 degrees, whatever you want, but that requires redoing the mesh and geometry. Or you can have a fix. You put your airfoil at 0 degrees like this, and then you change the incoming velocity. So I'm going to show you here first. Let's run the case. So if you go here, graphics, mesh, see that we have the airfoil, okay, rectangular domain, and we put it at 4 degrees. Okay, so for that here, it means that the physical angle of attack is to 4 degrees. So let's run this case. Okay, so the user, you follow your vertical workflow here. So let me start from the Turbulence model. So here we're going to use the K omega SST. Okay, so in the previous tutorial we didn't use this one. You can use it, but remember that you will need to update the inlet conditions. But in this case, let's go K omega SST and the false option. Okay, so you keep going here, materials. Okay, you set the properties, the air properties. Okay, the standard air properties is incompressible. Then here in domain, you come here and you double click here, and you can remember that you change the properties of different working fluid. You need to select here. Okay, and so some conditions, your operating conditions, you set your reference pressure, then boundary condition. Each of the boundary of the surfaces that you define here, you can define boundary conditions. So here we have just one inlet, outlet, and this one we set slip walls, and then the airfoil there, no slip walls. We keep here, then we go reference values. This is the values that we use to normalize compute coefficients, so remember to set this. And now methods, as usual, choose the default method. This is good, or a good option. Therefore, for this problem, this is the default proposed by Fluent. And then the relaxation factors, also the default values are okay. Then go report definitions and start to define all the reports that you want. So see here that we have just the y plus value, and then we have the lift and drag coefficient. But let me click here and see that when you click in drag, see that we have the drag is computed in reference with x and y. Okay, so remember that in the case that velocity here is centering like this, so the drag is parallel here and the lift perpendicular. Okay, and this is the convention I like to use. Okay, instead you use the other convention that you change the angle, you will need to update those angles. Okay, this angle here, when you compute the forces, you need to update. This is the direction vector. Okay, the unit direction vector. Descent, you will need to update that value here when you define your inlet velocity. And see that in this case we say magnitude normal to boundary, but you can give magnitude and direction vector. Okay, so nothing to do here. You have many monitors we can initialize. Okay, so let me initialize using values and let's run. Okay, so we run it. Okay, so residual CL, CD, maximum Y plus. So see that very fast solution. Okay, we get here everything is not it's not oscillating anymore. We can take it that the solution is steady, and your Y plus, see that this mesh is wall modeling. Okay, so now we can go here and check for some colors. So see that you have your static pressure, or here you have your velocity, and you can access all your variables that you have here. So for instance, you can plot turbulence quantities. Okay, so through kinetic energy, you can change here the range. So let's put 5 there. Let's see here that click to range. Okay, so where you have values, large values, okay, in red, let's say, is where the kinetic energy turbulence model is kicking in. Okay, and see that close to the walls. Okay, it is a non-zero value because we're using the wall function now, Y plus more than 60. So it's a non-zero quantity. The same way you can select here the turbulent viscosity. Okay, so out to range here and see that this is again give you the turbulence viscosity where the model is kicking in. Okay, so you go here, let me reduce this, and see here is where it is added. So see what you have here is that in these boundaries here, see that somehow the model, it is computed some turbulence viscosity there. Okay, so this is probably you will need to revise the inlet conditions or the wall. Probably I left the walls, top and bottom wall, I left those as I left in those one the slit conditions. Here I have no slit, so probably you need to revise that to eliminate that. But what is interesting to see here is that see that why it is important. So let me go back here to viscosity to put those walls far from the body, because in this case it might happen that if you have this wall too close, it might happen that will influence the solution here. Okay, so see that you have to be very careful. Okay, when putting this one. So usually the criterion is that you need to put those walls far enough so there are no gradients close to the body. Okay, so you have all your quantities here, effective viscosity, okay, turbulent viscosity ratio. Okay, so this one, let me go here. Okay, so this is the one that I think we were looking previously. Okay, so see that here. Okay, see this is what was the one that we were looking previously. So this is the ratio between the the molecular viscosity and the turbulent viscosity. And see here that if you look at this one, you might have the impression that something's happening here. Okay, but remember that here will be laminar. So and see here that in the wake you have where the model it is working the most, putting all the viscosity there. Okay, so auto range. Okay, so this is how you do you can access all variables, and then also remember that you can put you can plot the solution. Okay, here you have the plots, y plots. So XY plots, and see here that we divide it in suction and pressure side. And I like to do it like this, usually when doing airfoil, because here you have the colors and you see suction, pressure side, you have a static pressure, you can compute here the pressure coefficient, okay, or you can plot the Y plus value. So let's go into turbulence and plot Y plus. See that you have the value here, and see that airfoil, okay, you have the maximum value around 60, but it might be better to look now at the average value, okay? But see here, in that actually the average, you compute the average will be something about 40, okay? So remember that also you can go into here, surface integrals, reports, and you can compute those quantities. So you can go here, facet average, turbulence, worldwide plus here, and see that you get it, that you have an average about 32. So this is a world modeling mesh, okay? So see that now, instead of looking at maximum, you look at average. You have different a different perspective, okay, what is going on. So important set your monitors, and also how you set your monitor. Sometimes it might be a good idea to check maximum, sometimes it will be better to check average values, okay. So I prefer, I like to set up both then, okay, maximum and average, okay. So in this point, what we're doing is checking now the forces, okay. So here also you have the reports, okay, so you can go and compute your forces here, or you can come here in this reporting definition. I already have the definition here, so you just press compute, okay. So you have the same here, okay. Here you will have physical forces, okay, newtons, and here the coefficients, everything normalized. So see that here we have our values, okay, for, let's say, let me compute again. So this is for CD. Okay, let me put it here and there, and now let me go here again and do the same for lift coefficient, okay, and we have it there. So now let's compare, because we have experimental data for validation, okay. So in the files that you download, you will have all that data there. So as you go here, in this case, surface data, see that you have this there. And see that as you open this one, you have here your data, and now you can compare, okay? So see that the lift coefficient, you have a very good agreement, and usually getting the agreement with drag coefficients, the difficult ones. So see that there is some difference there, but kind of is around the ballpark, okay? We're there following the trends, but this is the most difficult one. And here, what it says that in this case we're using wall functions, and see that wall functions, they tend to be very accurate. There are some situations that it would give you some differences. So see here that we have a difference between experimental and the simulation, but also see that the experiments also there are some uncertainty. So see that the actual angle measured there is 4.04. Here we're precisely at 4 degrees, so there might be some influence there, but see that we have some differences. So it might be better to run, or you can run also at using a much finer mesh and see the differences. That much finer mesh will give you a closer agreement here, okay? So this is a relative large Reynolds number. Also, you need to be careful with the data that you're using. So see here that we're using trig transition, that is force transition. So remember what I say, that CFD simulations, they have the tendency to have a better agreement using force transition data. If you use natural transition, okay, these coefficients will be different. So here I think I have that data. So see here I have force transition, okay, for different methods, and see here that you have all these coefficients. And then when you have free transition, see that you have different coefficients. Okay, the largest difference here will be for the drag coefficient. Okay, so this is, if you use this data, you will have problems getting validating, because it tends to be you need more accurate meshes, solvers, and usually for natural transition, it's better to use, if you are interested in this one, a transition solver. Here we're using the traditional transition models. So this is the case, the first mesh, 4 degrees, and now let's open the other mesh. Okay, so if you go here, by the way, I forgot to say that in this case, I'm saving CD and CL. I chose to save the output here, report files in output files in text files. So as you go, whatever you're running the directory, you have the file. See here that you have these text files. So here you're going to have the iterative convergence. So it's always a good idea to save this one, but it's up to you, okay? So let's open the other file right here. And it's the same mesh, the same idea, but it's at 0 degree, okay? The physical angle, now we put it at 0 degrees here. Okay, so see that is there, okay, your mesh. And let's run this case. So the setup is exactly the same, okay? So see, again, we're saving all these files, okay? And let's go and let's run this one, okay? So basically you do like this, no, I want to override, just to construct this kind of plot, not to do the polars like this. So see that this is, you have it as an exercise, okay? You have here different results, okay? And now you can run your simulations using different models. So see here that I'm using K omega ST, okay? And see that here, we put it here and we can do our validation, okay? So the difficult part in CFD for airfoils is this, predicting well here the maximum lift, and also the stall pattern, okay? Because here, see that the stall pattern is abrupt, severe. It goes suddenly down, and see here that the tolerance model tends to be smooth. So this is difficult to predict, and here what you need to have the right prediction like this, you need to use transitional models, okay, that are more accurate in this region. But here in this linear region, any turbulence model will have the tendency to be very accurate. Okay, so see here, it's a very fast simulation. See that everything is stable, okay, as we are expecting here. Well, we have CD, CL, your residuals, and again, you can go here and start to plot colors. So see that symmetrical solution, you go here, your pressure, okay, you zoom in and you will see your boundary layer, but remember we're using wall functions, and your maximum Y plus is something about 45, but it might be better to check the average value, okay? So let's see what is the average value in this case. So we have XY plot, pressure, suction side, and let me go here and wall Y plus, and see that again, see it will be an average, something about 30 towards the trailing edge, probably will go in the buffer layer. But again, we can take this mesh for granted that is a good one. So to be sure, you can go and do the computation here, fast average, and see that we're in 30, okay? So it's this sweet spot, and we take this mesh as a good one. But now let's rerun this case, okay? But see what, just to show, I want to show you that this is very important when doing these kind of simulations, you know? And now let's say that I want to run back 0 degrees, okay? But I want to change this angle, okay? And I have the physical incident here 0 degrees, okay? So, okay, before setting that, okay, I forgot, you can compare also with the coefficients. So I put Hill there, I don't need the Hill. So you can compare your coefficients, compute monitors here, okay, with the experimental results. I'll see that in the case 0 degrees, see that in 0 degrees, the flow is there as attached. We have a very good agreement, okay? And you can do the same for CL, okay? Compute. And as you compare your CL with the experimental that you have it here, okay? See that CD and CL. CL, you have a non-negative value, so again, see that the angle is not 0, okay? And usually, but it is oscillating, but it's a very small value. So we have a good validation for 0 and 4, but what I want to change now is this angle. So the advantage, what is mentioned, the advantage of having this mesh, you put it at 0 degrees and then you rotate this angle, is that you can sweep all angles of attack, okay, without modifying the mesh. Instead, if you want to modify the geometry, you will need to do the mesh for each angle, okay? I prefer to do it like that, but it's up to you. We're going to see that there must be the same or similar results, okay? But the difference here, that look at your boundary conditions, okay? So you have inlet and outlet, but if we want to change now the angle, you need to also change the boundary condition. So now this is an inlet, but also this is an inlet. So we need to start to change the boundary conditions, and this will become outlet, outlet, inlet, and inlet. So you have to be careful, extra careful here. So let's go here and change that. So I know that the bottom will be now a velocity inlet. Okay, so I apply that, and the top, I know it will be a pressure outlet. Okay, apply. So it will be like this. Okay, the same. So see that we set everything. Okay, so see that you have inlet here, and the outlet, you have 2 outlets. Okay, so here you have your setup. So this is the thing that you need to do when you change the incoming free stream angle. So in this case, at the inlet, let's set up the value. So if you click there, see that now we choose magnitude in direction. Okay, so 90 meters per second with this curve will give you the range of that is 6 million. So see that now also let me choose that you need to give the direction vector. Okay, so this is, put it like this, and this. I already computed, you put it there, apply, and that's all. Okay, and remember also the initial conditions for the inlet value. So here I'm using relative high values. Okay, it might be better probably to choose lower values or rig the validation reference and see what values they are using. So in this case, we're using this paper. So I think it's what we recall that they're using lower values. So it might be better to use lower values. It's up to you, but see that this is all another source of uncertainty. So we define here the inlet velocity, and now let's do the same with the bottom. But here I have this option, copy, and I can copy from inlet to bottom. Okay, here it lets you see only the patches that have the same type. And now I copy those values automatically, so I don't need to redo everything manually. Then outlet, nothing to do. Here, nothing to do. And the walls in the airfoil, you have normal walls. So see that this is how you do your setup. Then you have to be careful also here in your report definition, because you need to update the reference angle here. Okay, so your references axis. So here that you go CD, okay, and now CD, you follow this notation here. So the drag direction, this is a rotation matrix now for your new reference system, is given like this: cosine of alpha and sine of alpha in radians. So let's put it here. So remember, put it there, cosine and sine. Okay, so I'm running for 4 degrees. See that I can compute it, and now it's giving me the value. Okay, and now you do also for CL. So CL, see here that you have the rotation. So you just put your minus sign there. And cosine. Okay, and you have your rotation. So this is fundamental step. Okay, otherwise you will have different different coefficients. Okay, so put it okay there, and you have all your setup. Okay, so if you have any other location in your case setup where that depends on these angles, you need to update it. Okay, so this case that is the only dependency here, and inlet velocity. So we change everything. Now let's recompute. So from inlet, and see that now, okay, what happened here, that it still doesn't see that angle. Okay, so okay, here make a mistake, it's here where it should be. Okay, apply. So sorry, okay, should be cosine sine. Okay, I put it in the wrong location, and the same here. Okay, is here where I should put that angle. Okay, so be careful of where you copy and paste. So now that I have that, I can go and initialize here for an inlet, and see that you have your direction vector. okay, in this direction, and the other up component going up, that it will define 4 degrees. Okay, so you have there, and now let's rerun. So pretty much you see that nothing changed, but it changed that you need to set up your new reference axis. And that's also see that you have your Y plus. So see that, recall previously we have this value, and then CL, CD, we have the same trend. Okay, so as you go here, compute, see that you have your CD, and compute, you have your CL. Okay, now you can compare with your experimental results. Okay, and now pressure here. So this is the thing that you have to take into account, that you need to remember when setting these cases. And let me check here, turbulence. You have to, I want to check this. I want to check this one. Okay, so here you have your turbulence viscosity ratio, and let me put 10 here. And see that you have the flow entering here with a given some given values. So see that you see the influence here, and this is very important. As you see, you set out this might give you different solutions, okay, the levels of intensity. So as I say, it's a good idea read the paper to see what values they are using, but I think these values are relatively high, the ones are using I am using. So let me put there 2 and 2, and here again 2 and 2, and let's rerun. Okay, so better will be in this case will be better to initialize again. Okay, so see that now this value change. Obviously it's been wrong. I think we're going to have different results. So see that we reinitialize, and let's see what we have. Very fast convergence rate. See that all your quantities are here. You have to report it here, and see there are maybe some slight differences. Okay, but you have your results. Okay, so this is a case. I really love these cases because here you can spend the whole week validating and testing different turbulence models. So in this case, we use the K omega. Okay, and you can do like in the previous case, you can now go K epsilon, try all the combinations, see what is the influence of in this case using every different K epsilon variant with different wall function formulation. So see that here the K epsilon you need to specify near wall treatment. Say K omega is Y plus insensitive. Okay, so this is the preferred option, or you have this parallel matters as well, so you can select that one. Okay, so this parallel matters is very good for external aerodynamics. Okay, so you can test it. So see that you have a small jump here in your coefficient, that it went up a little bit, but it's still there. The values are there, close to the experimental ones. So this is the in this case, okay, we have this wall modeling mesh, and let's now run again. But instead of using this rectangular domain, see here that we have this C domain. So let's use this mesh. So you can close this one, open the other case. Okay, so as you go the rectangular C domain, see here that you have 2 case setups, 0 and 12 degrees. I will go and open 12 degrees. So in this case, I'm not rotating the geometry. Okay, so as you go and you zoom in, you will see what I'm doing is rotating the inlet velocity. See that this is called C-grid because it has this shape of a C mesh. So this was using a structure measure. Okay, and see that this is a very nice mesh, very refined. This is wall resolving. Okay, and see that in this case, the angle, the physical angle of attack is always 0, but what changes the incoming velocity. So it's 12 degrees. So as you go here in the case setup, nothing changed. Everything is exactly the same. But here the inlet, you define your direction vector. Okay, so see that we have our direction vector. Okay, and see that in this case, the intensity level is set to 2 and 2 here. And okay, in the previous case, I was running at 90 pro, a little bit larger than the actual value. So that's why also they were coming a little bit higher. So you need to check all these dependencies. Okay, but what is interesting in this one also is this degree. See that the inlet boundary corresponds to all this. Okay, so you just need to set this. Okay, and then the outlet. You keep reading, you set reference values, everything, the report definition, see here that also computing moment, and didn't put here the y plus, so let's add y plus, or new surface expression, and I want to have the average, okay, in this case, and you select your airfoil, so see that the airfoil is a single surface, it's not divided in many surfaces, so I give it a name, average, and report to plot, and you have it there. Okay, you y plus average, you go initialize. I will use the hybrid initialization recommended method, and now we can run. Okay, so we're using in this case k omega SST standard method, and you press calculate, override, it will go there and run your simulation. You have all your coefficients, so see that CL, CD, CM, and Y plus. So see that this is a very, okay, sorry, I choose the wrong variable, I plot in there the average pressure, so I will update it. So see that now, in this case, we have a different convergence rate, okay? See the even the mesh can have an influence in your convergence rate. So see here that the residuals they look that they are stalled at the beginning, okay, then you have these oscillations, and then you let it run a little bit and see that now they are going down. So this is why also you need to let run the simulations for some time. So see that even though here it's not, you don't see any oscillation here, you cannot say that, okay, I will stop here. So when you see these behaviors, is that, and even if your residuals are not oscillating, it's a good idea to let it run to see if something happening. So this was like the turbulence model working a little bit. Okay, so now you let it run and see that here now it went down and you have the right convergence. Okay, so again, you can go here and plot your value. So somewhere here you have, so it's a very large domain. So that's, remember what I say, that user external aerodynamics, stuff like this, so they need to be very far from the wall, so the influence is negligible. So probably in this other case, it was a small domain, so maybe they will have an influence. Who knows? You need to quantify that, and you access everything here. So see that now you have the weight there, much nicer resolution, and we can go here and we can plot your quantity. So see the y plus, see that this is below 1, it's something about 0.2. Okay, so it's well resolved. So, and actually when we can go here and we can plot, if I go to turbulence variables, see that as you plot turbulent kinetic energy, see that now close to the wall, the value is 0. You are not modeling, you are resolving everything. So if you recall the previous case, you have the jump. You have a large value here, okay, it wasn't going to 0. In this case, goes to 0 because you are resolving. So you are integrating into the viscous layer, okay. So let me go 50. So you can see the progression, okay, from 0 to a peak value. Remember that they're throwing kinetic energy, and those will peak it somewhere in the boundary layer. So see that you have there all your progression. Same with all turbulence quantities. So I like to plot here turbulent viscosity ratio. Okay, and this one can give you, because this ratio can give you an idea of the edge of the boundary layer. Now usually you have it here, and this will represent your boundary layer. Not precisely, but can give you an idea. So you can use this one to control if you have a good mesh. Okay, and ideally, okay, you should have your mesh, okay, that should have a smooth progression in this region close to the body, okay, where you have this large difference, now this large turbulent viscosity ratio. Okay, it should be a smooth progression, so you are sure that you are resolving well any gradient that you have there. Okay. And as usual here, you have your coefficients. So see that we're much larger values, and see that we have CD, okay, 0.0147, and you have there your experimental data. So for 12, see that is, again, see that is 12.12 actually, not 12 precisely, but see that the values are there, okay, very close to the experimental one. And well, this is what you can do is just do a sweep of all angles from 0 to 20 and do the validation. Also, you can test different turbulence models. So this is also a beautiful case because you can try all models and see the influence, okay? So it will be a small influence in this case, you can try all of them. Generally speaking, external aerodynamic airfoils, the models to use is the spiral Almaras or the K-omega SST. You can also go and try this one. Okay, later we're going to address transition in another tutorial. And then also we're going to talk about these corrections using some airfoils. So at this point, okay, what else we can do? Okay, let's rerun, but now at 4 degrees. Okay, just to show you again, to remind you how the changes. So remember, you go here, and you should have your direction vector. So let's put our direction vector here and here. And remember, in this case, we're changing the free stream value angle, so you will need to update your report definitions. Okay, so you need to update the one for lift. Okay, so this is minus, okay, will be minus here. Minus sine, cosine, okay, for lift and also for drag. So cosine. So this one, as we are doing parameter studies, you can parameterize this with no problem. Okay, so we put it there, we updated the angles, now everything has been updated. We can go here and you can initialize. And now you press run and you are running at 4 degrees. Okay, so see that it's relatively easy to do this and sweep all angles. So now it's running. CD, CL, so everything is stable. This, I need to update this one. It shows the pressure, it shows the wrong quantity. And see that the scale is residuals and now going down. So see that in this case, the turbulent variables are the ones that are having problem converging. They have a slower convergence. So it might be an idea, probably this is nothing bad, okay, by no means, but if you start to have problems, see that here you can go and update on the relaxation factors. Might be the you might update this, okay? So we go here and now you have, okay, your quantities here, and see that this wall resolving mesh is you compare with your experimental results, your validation data for 4 degrees. See that now the drag coefficient is very close to this one, and your lift coefficient also very close. So see that when you want that extra accuracy and you don't have separation, adverse pressure gradient. So remember that here you have adverse pressure gradient, okay? So we studied these concepts in aerodynamics. Okay, so probably here, when you start to have adverse pressure gradients, it's better to have wall resolving. As you go wall modeling, recall that you have those corrections, okay? The wall enhanced. Here in K epsilon, you have the non-equilibrium wall functions that you can use. In K omega, you didn't have that option, but you can start to enable these corrections, okay? So, nice case. So I invite you to do from 0 to 20 to 24 or to 20. So see that the stall will be something about 18, and getting the precise stall can be tricky. You have your data there. So getting a good agreement here, linear Regina says easy. Okay, also in drag, getting this stall pattern, okay, that is tricky. But here we're using transition model. So see this circle here, this is the transition model, this is the spolar, the K omega SST. So this is all for this case. Thank you for attention. See you next video. Bye.